The geoid. We've probably all heard this term before, but do we fully understand what it is, how it's created, why and when we need to use one, and the error introduced by not using one, or even the error introduced by using one properly? If you use GPS or GNSS or the data that is derived from it, these questions are all extremely important to understand, and the cost of not knowing how to use a geoid properly can be very significant, as we will see in this video. I cannot state enough how important geodesy is for everyday surveying and the ramifications from not having at very least a rudimentary understanding of how we surveyors navigate the effects of the Earth not only being roundish, but also how much of a role gravity plays beyond just affecting the level bubbles we use in our level and instruments. This will be our first attempt at the third dimension to peel back the layers of the onion that is geodesy. So grab a coffee and settle in, because although this will get technical, it is vitally important. What is a geoid? Before we talk about exactly what a geoid is, I want to briefly discuss what a geoid model does. To put it very simply, a geoid model converts the ellipsoidal heights that GNSS uses to much more useful orthometric heights, more commonly referred to as elevations that are referenced to global mean sea level. We'll circle back to this, but to understand what a geoid is, it's important to know what a geoid model does. The standard definition of the geoid that is commonly used is: the geoid is the equipotential surface of the Earth's gravity field which best fits in a least squares sense global mean sea level. While we often think of the Earth as a sphere, our planet is actually very bumpy and irregular. The radius at the equator is larger than the radius at the poles due to the long-term effects of the Earth's rotation. And at a smaller scale, there is obviously topography. Mountains have more mass than a valley, and thus the pull of gravity is regionally stronger near mountains or areas of relatively higher density or mass. All of these large and small variations of the size and shape of the mass distribution of the Earth cause slight variations in the strength of the gravity's pull. If one were to remove the tides and currents from the ocean, it would settle into a smoothly undulating shape, rising where gravity is high and sinking where gravity is low. This irregular shape is approximated by the geoid, a surface which defines zero elevation. NGS, or the National Geodetic Survey, which is the agency responsible for defining and managing the National Spatial Reference System in the United States, currently has two different types of geoid models, one of which is gravimetric geoids. These geoids are defined by gravitational measurements taken from either satellites, airborne surveys, or terrestrial measurements. They are also often refined using DEM data. Some examples of gravimetric geoids in the US are XGeoid 19b or USGG 2012. The problem with these geoids is that they do not precisely fit any of the vertical datums used in the US. NAVD-88 being the most current vertical datum in use in the conterminous United States and Alaska. This is because NAVD-88, like other vertical datums that came before it, are entirely based on differential leveling and realized via hundreds of thousands of benchmarks spread across the country. NAVD-88's zero elevation isn't a perfect representation of an equipotential surface. So we need a geoid model that can convert ellipsoidal heights not only to orthometric heights, but orthometric heights that would align well with our current vertical datum. This is where the second type of geoid comes in, a hybrid geoid. Some make the argument that these are not true geoids and shouldn't be called as such. Rather, they should instead be denoted as transformation models or conversion surfaces. Geoid 18, the current geoid used in the conterminous United States, Puerto Rico, and the US Virgin Islands to transform ellipsoid heights to orthometric heights, is an example of this class of hybrid geoid. So how is it different from a true gravimetric geoid? Well, Geoid 18 uses the gravimetric XGeoid 19b as a base, but also data collected from a program by the NGS called GPS on Benchmarks, where members of the public, typically surveyors, went out and collected GNSS data on existing NAVD88 benchmarks. A total of 32,000 measurements were made, and that data was then submitted to the NGS to provide an estimate of the measured geoid height by differencing the GNSS measured ellipsoid height from the previously leveled orthometric height. These differences were then compared to the gravimetrically derived geoid model. If the residual of a particular observation met a certain threshold, that measurement was used to tweak the gravimetric geoid in the creation of the hybrid geoid. This resulted in a transformation surface that is currently used today to convert GNSS-derived ellipsoid heights to orthometric heights that align as best as possible to the current NAVD88 vertical datum. Geoid 18 isn't the only hybrid geoid currently used in the United States. Geoid 12b is currently used in Alaska, Hawaii, Guam, and some other island territories of the US. We now know what a geoid is, why and when we need to use a geoid, but how do we surveyors typically use a geoid? When creating a job in your data collector software, you'll have the option of pointing to a geoid model that is stored somewhere in the files of your data collector. If you're post-processing static data in Opus, it should automatically use the correct geoid model. And if you're post-processing your data in StarNet, for example, you just need to make sure you download and point to the correct geoid model in your project settings. The computations being made using the geoid model or transformation surface are fairly straightforward. The geoid model works hand in hand with a reference ellipsoid. In the case of Geoid 18, it uses GRS80 of NAD83. For any point on the surface of the reference ellipsoid, there is a geoid height assigned to it. Think of a DEM that just happens to be round, just like how every pixel on a DEM has an elevation value assigned to it. Now let's circle back and fill in a couple of holes that I breezed past. I mentioned that GNSS works with ellipsoid heights, but it's important to fully understand why that is and what an ellipsoid height is. An ellipsoid height, denoted by little h, is the vertical distance from the reference ellipsoid or three-dimensional geometric figure used to approximate the shape of the Earth to the point being measured along a plumb line normal to the ellipsoid. Ellipsoidal heights are necessary because when we use GNSS, we use a reference ellipsoid to provide a consistent and mathematically simple method of determining a position on the surface of the Earth. When looking at our measured point coordinates, we often see northings, eastings, and elevations when using GNSS, but those have all been converted from the geodetic coordinates on the reference ellipsoid that were in latitude, longitude, and ellipsoid heights into northings and eastings of whichever mapping projection we set, and the elevations being referenced to the geoid model being used. The problem with ellipsoidal heights is that the reference ellipsoid does not have any direct relationship to Earth's gravity field. This means that our traditional survey instrumentation, such as a differential level or total station, which we align to gravity using a level bubble, foot screws, and the tripod it's set up on, have no direct way of measuring elevations on the ellipsoid. Not only that, but since the ellipsoid ignores gravity, you could have a point at the top of a river and another point at the bottom of the river with water flowing between the two that both have an identical ellipsoid height, or even have a situation where water is flowing uphill in a sense if we are defining our elevations via ellipsoid heights. Because of these factors, ellipsoid heights, although necessary when using GNSS, aren't very practical to use in everyday applications. So we want to be able to convert those pesky ellipsoidal heights to something more practical. This is where orthometric heights come into play. We already know we use a geoid model to convert ellipsoid heights to orthometric heights, or do we? It's important to understand that in reality, we aren't directly converting ellipsoidal heights to orthometric heights or into NAVD88 using a geoid model. We are approximating orthometric heights using a geoid model, not directly converting them. There are two reasons for this. The first being because true orthometric heights are measured along a curved plumb line, which is affected by local variations in the gravity field. And the second being that the geoid model is typically approximating the vertical datum. Geoid 18 does not align perfectly with NAVD 88. There is error in the conversion, which we will look into further. Orthometric heights or elevations are much more commonly used because we know if there are 2 points with differing orthometric heights, water will flow to the point with a lower elevation as long as the force of any present wind or tides isn't great enough to offset the force of gravity. And lastly, a geoid height is the approximate difference between ellipsoidal heights and orthometric heights, or the height between the geoid and the ellipsoid that is normal to the ellipsoid at the point being measured. The three heights can be related to each other using the equation little h equals big H plus n, although again, it should be noted that this equation is only an approximation because of the fact that the true orthometric heights are measured along a curved plumb line normal to the geoid and every other equipotential surface between the geoid and the measured point, for which there are an infinite amount of these other geoids. For most practical surveying projects, this small height difference can be ignored when using GNSS. Just a quick note on nomenclature. If you hear the term the geoid being used, it is usually referring to the specific geoid that defines zero elevation in that specific area, as there are a multitude of geoids surrounding it. Every equipotential surface is technically a geoid. Luckily for us in the United States, Geoid 18 is relatively well defined. There are many places in the world that do not have access to an accurate geoid, and as a result, GNSS-derived orthometric heights are often not an option when vertical accuracy is desired. That being said, Geoid 18 isn't perfect. NGS provides a map of an estimated error between Geoid 18 and NAVD 88, and as you can see, it ranges from about 1.4 centimeters to 4.1 centimeters at one standard deviation of confidence. So what do these numbers actually mean? If I were to take a GNSS measurement at a point, I would not only have the inherent error of the GNSS measurement in the vertical axis that affects the ellipsoid height, but if I wanted the orthometric height at that point, which I would also have to take into account the error in converting the ellipsoid height to an orthometric height. An example of this is when we look at an NGS solution report, we can see a significant decrease in accuracy between the derived ellipsoid height and the converted orthometric height. We can actually look at a map that shows the Geoid 18 to NAVD 88 uncertainty across the conterminous United States, and it starts to really get interesting when we overlay the map that shows where the previously mentioned GNSS on benchmark observations were used in the creation of Geoid 18. We can see a very obvious correlation between GNSS on benchmark observations and the quality of Geoid 18. It is important to note that these uncertainty numbers reference the possible error of the conversion of an ellipsoid height to an orthometric height in terms of absolute accuracy. But when we're looking at height differences or relative accuracy, things look a little bit different. Because the sources of error that affect the geoid model at a particular location are somewhat localized, the uncertainty of height differences between nearby points is significantly smaller than the uncertainty of the absolute heights to each point. To put it another way, if I set up a base station on a nearby NAVD 88 benchmark that was defined very accurately and took a GNSS observation to another point that was relatively close to that base setup, the resulting error for that orthometric height of the measured point would be significantly smaller than it would be had the base been much further away. Of course, we would already expect the ellipsoidal height to be improved by the smaller RTK baseline, but since the errors affecting the geoid should theoretically be similar at both points, the error due to the ellipsoid to orthometric conversion, aka the geoid height, are minimized. How much so? Well, that's a bit more difficult to give exact numbers on, as we just saw the quality of the geoid varies dependent on location. According to the paper, Guidelines for Establishing GPS-Derived Orthometric Heights by David Zilkowski, Edward Carlson, and Curtis Smith of the NGS that was published in 2005, and I quote, "Geoid height differences can be determined in select areas nationally with uncertainties that are typically better than 1 centimeter for distance up to 20 kilometers and less than 2 to 3 centimeters for distances between 20 and 50 kilometers. Keep in mind, when this quote was originally made, Geoid 18 did not exist yet. Considering Geoid 18 is an upgrade to previous geoid models in terms of accuracy, the assumption that these numbers may be even better today would not be unfounded. One should also note the statement, in select areas. These values may not be as accurate in mountainous regions where geoid height uncertainties are typically larger. There's one last thing I want to talk about in this video because I've seen this issue more than once before. A crew goes out, uses RTK to stake out some points, but forgets to apply a geoid model when initially setting up the job. Was their data meters out because they weren't able to convert the ellipsoid heights to orthometric heights and a value of 0 was used for the geoid height? Not quite. The measured orthometric height at the rover is equal to the orthometric height of the base converted to an ellipsoid height plus the delta ellipsoid height between the base and the rover. Then the ellipsoid height at the rover is then converted back up to an orthometric height. But in this situation, the base station's elevation isn't adjusted down to an ellipsoid height and the rover elevation isn't converted back up to an orthometric height. So we're basically just adding the delta ellipsoid height to the base's orthometric height, which means that if there is no change in geoid heights between the base and the rover, then we're fine, no error is added. But this is rarely the case. And typically as the distance between the base and the rover increase, so does the change in geoid heights. By how much? Well, it depends on where you're at on the Earth because as we discussed earlier, the geoid is an amorphous surface that has peaks and valleys. NGS has a Geoid 18 height computation tool that we will use to look at a few examples to help assign real numbers to this problem. We'll look at 2 points 100 meters apart down here in Florida where the geoid doesn't change that much, and 2 points 100 meters apart in Wyoming where the geoid changes quite a bit. This will give us an idea of the possible magnitude of error with a nearby local base station. In both of those situations, we'll also extend those baselines out to 10 kilometers to get an idea of the magnitude of error we would be looking at in a situation where we were using a nearby chorus for RTK. For the 2 points 100 meters apart in Florida, the difference in geoid heights is less than 1 millimeter. When we extend the baseline out to 10 kilometers, the change in geoid heights jumps up to 67 millimeters. So not applying a geoid in this particular place in Florida probably won't have any significant effect when running a local base rover on a very small site, but if you're receiving your corrections from a further off-site base, you'll start to get some sizable error creeping in. For the 2 points in Wyoming, however, it was a different story. At 100 meters apart, the change in geoid heights was 7 millimeters, and at 10 kilometers, the change in geoid heights was 735 millimeters. If you are working in an area like this, even when using a local base on a medium-sized site, you could be introducing significant error. And if you are using an off-site core station, you would be looking at some very serious error being introduced by not applying the correct geoid. With the ease of use that GNSS has brought to our industry, we can sometimes fall into the trap of becoming button pushers without fully understanding what is happening behind our screens. We must remember that there is far more to the question of how accurate our GNSS measurements are than the precisions listed on our data collectors. When we need to bring an elevation to the site, we have a choice to make. Do we spend the time to run a level loop from the closest published benchmark to a new control point on site, or take a GNSS measurement on the site control point and convert the GNSS derived ellipsoid height to an orthometric height. The level loop will almost certainly provide a more accurate result, but considering the GNSS derived height will be much quicker, will the resulting elevation be good enough? That is a question you as the surveyor must make based on the accuracy requirements of the job at hand. Hopefully this video shed some light on the accuracy implications of using GNSS to derive orthometric heights and provided some insight on how to do so properly to help you make that decision. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.